Hello students, this is Mr. Ezra. Today we are going to be talking about some applications of these exponential and logarithmic functions that we've been talking about, at least to some degree. So I want you to notice that we have some formulas here at the top. This is exponential growth, and the one on the right is exponential decay. It's likely that you've seen these in your science classes or you've seen these in math classes in the past. P is a principal. It's like the starting amount, the amount of whatever it is that you start with. We find the rate of increase or decrease depending on whether it's growing or going down, decaying, and we add 1 if it's growing and we subtract from 1 if it is decaying. And then T is the amount of time, usually in years. So this is a basic exponential application problem. We have 20 grams of carbon-15 stored in a container. The amount in grams of carbon-15 present after T years decreases by 1.2%. Now, before we jump into this problem, let's see, I think I've got a picture of, there's some carbon right there. You can see what it looks like. Carbon has many isotopes. Some of them are stable and they will last a long time. Carbon-15 actually isn't one of them. So carbon-15 has a half-life of about 2.5 seconds. Pretty unstable. It's not as unstable as some of the others that have a half-life of milliseconds. Carbon-14 has a half-life of 5,700 years, so it's a bit more stable, and 12 and 13 are stable. So I'm kind of pointing this out in one way, just to think. I think it's really cool if you have kind of an interest in science and chemistry to understand things a little better, but also to state that this probably isn't a true statement. It probably, maybe there's some special container, and in this special container, then it's going to decrease by 1.2% a year. But in truth, I believe, you can ask your chemistry teacher to make sure, I don't really know, 20 grams of carbon-15 probably wouldn't last that long. I don't think it's a stable element, and I don't think it would last that long. But let's pretend. A lot of times we play in a world of pretend in our math class. So let's pretend that 20 grams of carbon-15 is in a container, and in this special container, the amount decreases by 1.2%. Is this a growth situation, or is this a decay situation? Well, when it's decreasing, that is a decay situation. We're decaying by 1.2%. Now, when we talk about our formula, right, we know now that we're dealing with decay. Our P is given here. How many grams did we start with? What is our principal amount, our starting amount? Well, it was 20 grams. So we know that we're starting with 20 grams. We can kind of write that off to the side. The R, which is the rate of change, essentially, is going down by 1.2%. Now, we can't use 1.2% in any calculations. We've got to change that to a decimal. So you can divide 1.2% by 100 to get 0.012. And that's the actual number that we're going to use, the 0.012. So part A says, write a model for the amount of carbon-15 present in the container in terms of years since being contained. Write a model. All right, well, I think we have enough information to write that model, right? We know that A, that's the amount that we're looking for, is going to be our principal. We know our principal is 20. It's decaying, so we're going to say 1 minus 0.012 is our rate of decay. Well, how much we're going down, our rate of change, really. And T is the time in years. That's our variable. That's the thing that's going to change. Now, we can simplify this a little bit by subtracting 1 minus 0.012 to get A equals 20 times 0.988 raised to the t. So this is a function, an equation that we can use for most of the other questions from here on out. Part B, how much carbon is present after 1,500 years? Well, we're told the amount of time in years is 1,500 years. What we want to know is how much, what is our A? How much, what amount are we going to have after 1,500 years? So we're going to use our equation that we just created, 20 times 0.988, and we're going to raise that to the number of years, which is 1,500. Okay. Well, put this in your calculator. Go ahead and calculate it out. I believe if I've done my math correctly that you're going to get a teeny tiny number. There is 1, 2, 3, 4, 5, 6 zeros, if I counted it right. 3, 4, 5, 6, before we get to 2, 7, 3. In fact, in your calculator, it's probably going to be 2.73 blah, 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 and then there's probably an E, letter E, which is like times 10 to the negative 7th power, which means that you're going to move that decimal to the left 7 places to get your actual answer. And this is still in grams, So there's not much left, is there, after that amount of time? A very tiny trace amount is still left behind. All right, it says, how long will it take for this carbon 15 isotope to reach its half-life? Well, when we say half-life, we kind of are talking about the amount of time that it's going to take for it to become half of what we started with, right? So we started with 20 grams. What would half of that be? That's what we were going to end with, half of 20 grams, which is 10 grams. That's half of 20, half of what we started with. So this time when we plug into our equation, we're going to start with A. We know A to be 10. And then we've got 20 as our principal times 0.988 raised to the, and this time the question is, how much time is it going to be? We don't know. We've got to figure this out. We've got to do it. So you should say, well, how in the world do I do this? I've got this exponent thing, and oh, wait. Didn't we just learn how to solve for the exponent by using logarithms? Just like earlier this week, we did, didn't we? The first step was to isolate the base and the exponent. So the 0.998 raised to the t needs to be isolated, which means we have to get rid of the 20. How do we do that? We divide by 20 on both sides. Which, you know, what should happen over here is this should be half. It's a half-life. So we'll end up with 1/2 equals 0.988 to the t. Okay, so kind of coming over here. Now, from here, we have to write this exponent as a logarithm. What is the base of our logarithm? It's going to be the base of the exponent, 0.988, right? Log base 0.998 of 1/2. That's what's inside, equals the exponent, equals t. So to solve this, I have to put this in my calculator. Now remember, if you have the log base command in your calculator, you hit math, you got log base, you can put this in the way that you see it. If not, you have to use change of base. Change of base is pretty simple. You're going to, in your calculator, take the log of 1/2 and divide by the log of 0.988. That's the change of base. Log of what's inside divided by log of the base. And I'm pretty sure that when you do that, you get something along the lines of 57.415 years. It's going to take a while to get to half. Question D says, how long will it take it to get to 5 grams of carbon-15? So let's scroll up a little bit. All right, 5 grams of carbon-15, that's now our amount, right? That's our A is given. It's 5 grams. And the question is how long? So we want to know the time. So we're starting with, not starting with, but we're ending with 5 grams. We're still starting with 20 grams. We still have the same decay rate. And we're going to solve this one exactly the way that we solved the one above it. We'll first divide both sides by 20. 5 divided by 20 is 0.25, or 1/4. We're going to take this exponent and write it as a logarithm. It'll be log with a base of 0.988 of 0.25 equals the exponent t. And then we'll use change of base again, unless you have the special function on your calculator that allows you to not have to use change of base. In that case, you can use that. It doesn't really matter. Just log of 0.25 if you're using change of base divided by the log of 0.988. And that is approximately 114.83 years. How did you feel about that question? Hopefully not too bad. Hopefully it was good. Let's go on to example 2. I'm going to scroll now. All right. Did any of you have relatives that collected Beanie Babies? Let me show you what we're talking about here. Let's see if I can find a picture of some Beanie Babies. So this is a picture of some Beanie Babies. Maybe in the late 90s and the early 2000s, these things were like insane. People were collecting Beanie Babies thinking, I'm going to make money off this one day. And probably you have a relative who has in their closet a big like tote or box full of these things that are not worth much at all. I mean, they really didn't retain their value. They were like a fad kind of a thing. I know I have relatives and I had friends, girlfriends, and friends in college that had some of the Beanie Babies. They thought they were cool. It was a big deal. People collected them. So in this situation, what we're saying is that at the time, back in 1990, when they were really hot, I mean, like you could buy rare ones. They were expensive, right? It's like buying like a rare baseball card or something. There was such a demand that these little stuffed animals skyrocketed in value. Again, we're going to make believe here a little bit. This might not be exactly true. But let's pretend that Katie bought a Beanie Baby, a special Beanie Baby, for $10. And then the stuffed animal's value increased at a rate of 7% per year. So she's holding on to it. She's hoping that eventually she's going to put her kids through college with this Beanie Baby. Maybe. Well, let's write the exponential growth model for the value of the Beanie Baby in terms of the number of years since the purchase. So again, I'm going to scroll down here. This time we're talking about growth. You'll notice that it's the same formula except we're adding R instead of subtracting R. So A, that's our final amount that we don't know. We know the starting amount, right? The amount of the cost or the amount of money the Beanie Baby was worth when she bought it because it is exactly $10. So we'll put a 10 in there. Our formula says add the percent of growth as a decimal. Okay, well, if it's 7% growth, what's 7% as a decimal? 0.07. So we're going to add 0.07. Okay, so we know it was worth $10. The rate of change is increasing 7%, or 0.07 raised to the t. Now we can simplify this a little bit by adding 1 plus 0.07. That's 1.07. raised to the t. So this is the simplified formula that we'll use. Okay, so let's see, what was her Beanie Baby worth after 2 years? We're asked, what's the value? What is A after t after amount of time of 2 years? All right, well, A is what we're looking for. We started with a worth of $10. It's increasing 7%, so 1.07. And we want to go for 2 years. Okay, well, calculate that, put that in your calculator, check it out. I believe that we're looking at $11.45. So at this point, she's not paying for college for her kids with this Beanie Baby. It's gone up $1.45. The next question says, well, how much would this Beanie Baby be worth today? Well, we got to think about this just a minute. Okay, today's year is 2016, but this Beanie Baby was bought in 1990, right? So it's almost like saying we're starting time at 1990, and we want to know from 1990 how many years is it going to take us to get to 216. Well, if we take 216 and subtract 1990, you get 26 years. So t is 26 years, right? 26 years after she bought it, after 1990, that's our t. That's how much time has passed. We want to know what is the final value, or what's the value at that point. What is A? So we'll plug these things in. A is, in our formula, A is $10 times 1.07 raised to the 26 years. Okay, now this is exponential growth. These things kind of increase quickly. So I don't have this one calculated out already, so we'll do it together with our calculator here. 10 times 1.07 raised to the 26th power. Huh. Well, Beanie Baby is worth a little bit of money. It's now worth $58.07. Not paying for college still, but it's increased in value a bit from $10. So, you know, if she had a whole bunch of these things, maybe she'd have enough money. Part D says, how long did it take for Katie to double her original investment? Well, her original investment was $10. What would double that be? Be $20, right? And we want to know how much time is going to take for us to get there. So this is another one where we're kind of going to be working backwards. We know that the amount that we're looking for is 20. We're starting with 10. Rate of change is 1 plus 0.07. We're going up 7%. And the variable this time that's left is t. So this is like the questions a minute ago where we have to work backwards. We're going to have to divide both sides by 10. 20 divided by 10 is 2. Okay. And 2 is equal to 1.07 to the t power. We're going to write this as a logarithm. Log base 1.07 of t. This is that swoop method that I use. Remember, the base of your exponent's the base of your logarithm, and then you swoop to the other side, and your exponent is your answer. So log base 1.07 of 2 is equal to the amount of time. Now, you can put this in your calculator if you have that log base function. If not, use change of base. It's just as easy, really. It's the log of what's inside, 2, divided by the log of the base, which is 1.07. I'm putting these parentheses in because when you put it in your calculator, you have to close this parentheses here before you divide, or you'll get the wrong answer. I did this before earlier today, and I got 10.245 years. That's a long time for it to double. So, 7% growth is certainly growing, but it's not growing very quickly, is it? Not unless you have a lot of money invested.